How do we prove that a sequence converges to a given value? Today we're going to do a sequence convergence proof for this example, which appears in Ross's elementary analysis. We need to work from the definition of sequence convergence. There are other tricks, but this is a lecture about how do we use the definition to get this job done. So we're going to work from this definition. The limit as n goes to infinity of an is equal to L. This means for every positive epsilon, there exists some cap n such that for every little n in the naturals, if little n is larger than cap n, then the distance between an and L is less than epsilon. So in simple language, this really means however close you want the sequence terms an to be to L, where the proximity is given by epsilon, then the sequence terms are eventually that close. After some point, then all of the sequence terms beyond that point have this feature that they are within that distance from the target value L. So we're going to try to use this definition of sequence convergence directly on this limit to calculate the value of the limit and prove that it's equal to its value. Now, we're going to guess the value of this limit, which might seem a little bit reckless, but because we're about to produce a proof of correctness, and it doesn't matter whether we are absolutely certain as we begin this proof, we should be certain by the end of the proof if the proof is correct. So how should we guess the value of this limit? As n approaches infinity, n cubed is huge, n is huge, n cubed is huge, 6 is rather small. And so we can see that the terms of importance here are the n cubed and the n cubed here, but n cubed is much larger than 3n. And so when we're thinking about very, very large values of n, we may ignore these terms. And if we ignore these terms, then this simplifies to 4n cubed over n cubed, which is simply 4. And so we'll guess the value of this limit to be 4, and we'll attempt to prove that it is equal to 4. Of course, that was not very secure reasoning, and if that reasoning was incorrect, because we were just discarding some of these terms, and that's not very precise or rigorous, if that reasoning was incorrect, then we won't be able to prove it. But if we're eventually able to prove it, well, then no worries, we'll know that we were right. So we're going to try to prove that this limit is equal to 4. Now, in order to prove that this limit is equal to 4, we need to exactly follow the definition of the limit. And the definition of the limit is in this logical form. And there's only one way to follow that. Well, there are many ways, but there's a straightforward way to follow this form as we write the proof. This begins for every epsilon. In order to begin a proof about every epsilon, we should let epsilon be a fixed arbitrary value greater than 0. It continues there exists a cap n because it says there exists a cap n, it will be our obligation to provide the value of cap n. It continues for every little n in the natural numbers. In order to prove something that continues for every little n in the natural numbers, we'll have to let n be natural. And then we have an implication to prove, and we'll do that by assuming this and proving this. Now, the hardest part about this proof is the second part. It's easy to say let epsilon be positive, but then we need to choose the exactly correct value of cap n. We won't know how to do that immediately, and so we're just going to leave a blank space in our proof for that choice, and we're going to try to fill it in later. And we're going to get more and more information about the correct value of cap n as we continue the proof, and then after the fact, we're going to fill that in. So let's begin in a straightforward way, trying to follow the structure of this logic in order to produce the appropriate proof structure. So let's begin. Proof. We're going to say let epsilon be greater than 0. Basically, we mean epsilon is any positive number. But the interesting values of epsilons are the ones that require this thing to be close to L. And so you want to think that epsilon is a very small positive number, which is requiring an to be very, very close to L in this final definition. So let epsilon be positive, and then we're going to need to choose n. Now, it's premature because we haven't done any algebra. We don't know what to expect. It's premature to hope that we can actually choose the value. But I want to illustrate that logically, this is where the choice has to be made. And because it's made here, it may depend upon epsilon, but it can't depend upon anything else because at the moment we choose n, we know epsilon, we don't know anything else about this proof. Now, the next start, so assuming this has been done, then the proof can continue. Then the next part is we need to prove, this thing continues for every n in the natural. So we're simply going to say let n be in the naturals. And then having chosen the cap n and having introduced the arbitrary little n, then we need to prove this implication. If this, then this. So of course, how do we prove an implication? We assume this part and we prove this part. So our next assumption is assume that little n is greater than cap n. Now comes the hard part. We have no idea how we're going to prove that this is less than epsilon, and we haven't even shown a value of cap n that will be the reason ultimately why it's less than epsilon. Nevertheless, we're going to start with this expression. So an is this sequence term here, and L is this 4. So I'm going to take this thing and I'm going to subtract 4. I'm going to put it in absolute value signs, and I'm not going to assert that it's less than epsilon, at least not immediately, not yet, because I have no reason as yet to think that it's less than epsilon. But I know that this thing minus 4 absolute value is what we need to calculate. So I'm going to continue here with a calculation of that sequence term minus 4 absolute values. So I don't know how this is going to work out, but I know that this is the term that needs to be calculated. Now, we're going to start some algebra, and we're going to start computing from here. And we're going to say equals, this thing is equal to something else, is equal to something else, is equal to something else, is equal to something else. And then eventually, we're going to continue on this side. And then eventually, we're going to get that this is, shall we say equal to epsilon? No, because we're not saying this is equal to epsilon. Eventually, we'll do calculation equals, 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 equals. And so let's fill them in just sort of provisionally. This is going to be equal to things, which is equal to things, which is equal to things. And then it's equal to things and equal to other things. And then we're going to continue here. And then eventually we're going to say less than epsilon. And as you write your proofs, I advise you to start with less than epsilon in the bottom right-hand corner. We don't know how long the proof is going to take, but we know that eventually this thing has to be shown to be less than epsilon. Now, if these are truly all equal signs, then great. This structure of the proof will demonstrate that this thing is less than epsilon. But we might not have the luxury of computing it so easily that every one of these is an equal sign. We have a little bit more freedom here in this proof than we're using, because this structure of a proof will demonstrate that this thing is less than epsilon, so long as some of these are equal signs, and some of them could be less than signs, and some of them could be less than or equal to signs. So mixed in here with the equal signs, we could have some less than or equal to signs, and we could have some less than signs, and we could have some more equal signs, and basically any sign which is compatible with this less than sign would be fine. We can mix in equals for the algebraic manipulations here. We're going to do a common denominator and simplify this fraction, and we can have equals for that. If we're making some changes to simplify things, then we can have less than for that. So we're going to have a long chain of, well, relationships between this term and the next term in this computation. And the key about these relationships is they have to line up so that eventually this is less than epsilon. If any one of these symbols is greater than, or if any one of these symbols is greater than or equal to, then it's game over, because then they won't chain together to demonstrate that this thing is less than epsilon. So we need to be strict about our attitude here. And as we do this, we're going to sort of build out this proof with the attitude that we are allowed to write less than or equal to. We are allowed to write less than. We are allowed to write equals. But those are the only relational symbols that we're allowed to write. And then finally, we'll get up to an epsilon here. And finally, we'll deduce the right inequality that we need. So the way I think about it, this term has a certain size, and we will eventually compare that size to epsilon. The size is allowed to inflate a little bit, but it's not allowed to exceed epsilon. So we're going to conservatively allow this thing to go up. It's allowed to, each time we move forward to the next step in the proof, it can stay the same, equals, or it can go up a little bit, less than. So this thing would be less than the next term. So as we work here, the way I think about it, this term is going to be computed and computed and computed and stay the same. And then if we need to, we'll allow it to go up a little bit. But conservatively, we don't want it to be up to 1,000,000, because then it won't be less than epsilon. So we have to be a little bit conservative about how much we let it inflate. And there's a little bit of an art to this. All right. What there's not an art to is a bunch of ugly algebra in which we calculate the common denominator of this fraction and join it together into a fraction. But this is not particularly difficult. Let's just go ahead and do it. I think I want to organize this so that I'm continuing in this direction and then this direction, and then I'll use that whole column there, and hopefully that'll be enough room for us. So we're going to introduce common denominator, and then we're going to combine this fraction. So let's do that real quick. I need to write this 4 as, I need to multiply this 4 top and bottom by n cubed minus 6. So let's rewrite this thing, and that's 4n cubed minus 24 over n cubed minus 6. So that the 4 has been multiplied by n cubed minus 6 and divided by n cubed minus 6 for the purpose of making a common denominator for these fractions. And then that'll continue in this direction. So now I can merge the fractions. And notice, of course, the 4n cubes will cancel. And we'll end up with a 3n minus 24. So that's 3n plus 24. And n cubed minus 6. Now, when we have a look at this term, we'll notice that the denominator has a 3n, and then, the denominator has an n cubed, the numerator has a 3n. And 3n is going to be a lot smaller than n cubed in general, which means this term is going to get small, which is good because we want it to be less than epsilon, and epsilon is just some number greater than 0. So this thing indeed should be getting small, and that's the behavior that we're hoping for. However, there are no further obvious simplifications. There's nothing obvious that we can do here to say, oh, well, this will cancel, right? These terms can't be canceled individually. We could imagine factoring the polynomial and canceling, but the factors here won't cancel any of the factors here. And so at this point, we've done the obvious algebra, and there's no obvious simplification. And so, well, it's going to start to feel a little bit stuck if we're just going to continue doing algebra with equalities. So we need to do something else. The annoying thing here is I would like to cancel terms, and I would like to simplify this, but these terms don't cancel as they are. This 24 is kind of annoying. The basic problem here is that the behavior of the addition and the subtraction and top and bottom and the behavior of the division, they kind of don't play well and don't simplify each other very well. So it would be nice if this 24 was the kind of term that could combine with this 3n. Now, right away, we have an option for how we can get these terms to combine. We can change the 24. We're allowed to change the 24 to anything bigger. The reason we're allowed to change it to anything bigger is because, well, that will cause this thing to grow, and that will give us the kinds of equalities that we are allowed to tolerate here. And so we can change this 24 to something bigger. And something which is bigger would be, for example, an n. Well, is this true? Let's write it down and let's see what happens. So this would not be an equals. This would be a less than, with the idea of changing the 24 to an n. Now, is that really true? Well, I've changed the denominator of a fraction, and that's positive, okay? And I haven't changed the denominator of the fraction, which is, well, it looks positive, n cubed compared to 6, but we might worry that the denominator of this fraction would be negative. Well, maybe we don't need to worry about that because of the absolute value signs, or maybe we do. So it's not quite clear what's going on with this fraction. Instead of changing this thing to an n first let's deal with the absolute value signs and see what happens. Here's a kind of a great idea. Instead of changing this 24 to an n, what would happen if we just dropped the absolute value signs? Now, is this true? Well, you can't just drop absolute value signs. That's an important function applied to this thing. But you can if you know this is positive. So do we know this is positive? The numerator here is greater than 24, and n here is a natural number, which means that it's 1 or larger. And so this thing is definitely a positive numerator. The denominator, unfortunately, is not always positive. When n equals 1, we get -5. When n equals 2, then it's already positive, and it remains positive for larger n. So here we have an annoyance here. At n equals 1, we have an exception, which means we can't actually drop these absolute value signs. For all other n's, this would work. So what we're going to do here is we're going to just go ahead and drop them, but we're going to remember that this actually requires something of n. And so what I'm going to do is I'm going to star this equality and with a requirement on little n. This requires that n is greater than 1. Now, technically 1.1 wouldn't work because then the cube would still be this cube would still be less than 6. But remember that n comes from the natural numbers. So being greater than 1 means that it's greater than or equal to 2, which is large enough. So that allows us to drop the absolute value signs entirely, and then we can just reason naturally about the fraction, whether it's positive or negative. And it also gives us, so long as n is greater than 1, then this equality is true. Now, are we entitled to do this? This is in the middle of the proof that we're adding assumptions that weren't justified at the beginning of the proof. So normally we are not allowed to do this. And in a sense, we've incurred a sort of a logical debt here. We're assuming something, but we don't have a justification for that thing that we're assuming. And so we're going to have to pay back that debt later. In fact, we're going to have to pay back that debt earlier as we go back in time and change the value of capital N here. But let's worry about that later. We're going to continue the proof. We're going to write down the requirement here for little n, and we're going to do what we want to do with it, which is to say that this thing is equal to this, which is true provided that little n is greater than 1. So this is our first requirement, and we're going to be accumulating these requirements as the proof continues. The next thing I want to do is I want to worry about this 24. So because little n is greater than 1, then it's at least 2, then the denominator is positive, the numerator is positive, and this 24, I wish that I could combine this term with 3n. And so what I'm going to do is I'm going to change this 24 to an n. Now this might seem a bit crazy, but the thing is, we're allowed to introduce an inequality. I'm allowed to introduce an inequality of the form less than or equal to. And so I'm allowed to make this thing slightly larger. Now, does that make it slightly larger? Well, both numerator and denominator are positive. So increasing the numerator will cause the fraction to get bigger. Does changing 24 to n make the fraction bigger? Well, yes and no. It only makes the fraction bigger if n is bigger than 24, which we have no reason to believe that it is. But no matter, we're still going to say that this is a less than, and that we're going to add this as a requirement on n, the requirement being that n is greater than 24. So provided that n is greater than 24, then, well, n is greater than 24. And then we have the truth of the statement that the replacement of 24 with an n causes us to have a less than symbol there. The reason for this replacement is that it causes some convenience to us. It allows us to join the terms 3n plus n into 4n, and then we have fewer terms on the top. And we're hoping to work for cancellation. Now we have a trivial little inequality here. I'm going to combine those to make 4n. Now we have two terms in the bottom of the fraction, and we would like to combine them, but of course they don't combine either. Now, this 6 is the sort of lesser term. It's the least significant term. This n cubed feels like the significant term here. If the 6 were 6n cubed, then that would actually be better in a way because we could combine the terms. But it would also be bad because it would mean this thing would actually turn out to be negative and our prior logic would be wrong. So we don't want this to be negative, but we would like this 6 to change into something which will combine with the n cubed. We could think that the 6 could change into something crazy like, for example, n cubed minus n, and that would cause a cancellation here, which would result in the bottom being just n cubed minus n cubed plus n, which would be n. But that would cause so much cancellation that this thing would be 4, and 4 is not necessarily less than epsilon. So we want to change this 6 to something which will merge together with the n cubed, cause some cancellation, but still make it so that the denominator of this fraction is a lot bigger than the numerator of this fraction. You see what's going on here that's really important to us is that we have an n cubed, which is going to cause this denominator to shrink. It's going to cause the fraction to shrink to 0 because the denominator is so much larger than the numerator. So we need to change the 6 to something that will allow us to combine the terms without destroying the basic properties of this, that it is a cubic in n and it goes to infinity. So the plan is to change it to some constant times n cubed. Now, here we need to think very, very carefully about the inequality that we're allowed. I can't change this. I must have this a less than sign. I can't put a greater than sign. So if I do this wrong and end up with a greater than sign, it's game over. So I am allowed this less than sign, and we need to think very carefully about what I'm therefore allowed to do to the fraction. So this is a positive number over a positive number, and I'm allowed to let the fraction expand. Because I'm manipulating the denominator, if I'm allowed to let the fraction expand, then I'm allowed to let the denominator contract. I can make the denominator get smaller. But this 6 is subtracted from the n cubed. And if I want the denominator to get smaller, or if I allow the denominator to get smaller, the thing subtracted from this n cubed can get larger. And so my plan is to make this 6 larger. So let's recap. I will make the 6 larger with the intention of making the denominator smaller with the intention of making the fraction larger, which will be the right inequality. Okay, so in my mind, I work from the inequality first because I know I have to end up with a less than, and then I work to what happens with this 6. So just to recap, because we expect a less than, because we demand a less than, the fraction can increase, the denominator can decrease, the thing subtracted in the denominator can increase. And so if I change this 6 to any positive multiple of n cubed, then I will have something which is bigger, at least for the right values of n. But I can't make it like a 6n cubed, because then I'll end up with a negative thing here, which is not what I want, right? So then it won't be greater anymore, right? So I need to make it so that these things combine and give me something still positive. Even 1 would not work. I'd have 0 in the denominator, but 1/2 will work. However, did I really make that bigger? Is 1/2 n cubed bigger than 6? That's what I claimed that I was trying to do. Did I actually do that? Well, when n equals 1, it's not. When n equals 1, 1/2 n cubed is 1/2, which is certainly not bigger than 6. So that didn't work. When n equals 2, it's again not. 1/2 n cubed is 1/2 8, which is 4, which is not bigger than 6. So that didn't work. But when n equals 3, then I get 1/2 27, which is 13.5, which is indeed bigger than 6. And when n is larger than 3, then it remains bigger than 6. And so here I've incurred another condition on n. It has to be bigger than 2. It has to be literally bigger than or equal to 3. Now, arguably, this condition is redundant with this condition up here. If we already know that it's bigger than 24, then of course it's bigger than 2. Nevertheless, I think it's best to write the condition that guarantees this inequality right next to this inequality. Later, when we have actual justifications for these conditions, this will be an important part of justifying this inequality. So here we have the next inequality, which is helping us simplify this. And so we get 4n over n cubed minus 1/2 n cubed, and that is slightly larger than this. So of course, the purpose of this is to allow us to combine the bottom terms, and we're going to combine them with some simple algebra, which will give us an equality coming up next. So that equality is 4n divided by 1/2 n cubed when those get combined, which is, I can move that 1/2 upstairs, and I get 8n over n cubed. And then that simplifies, of course, to 8 over n cubed. Now, that's about as algebraic, I did that wrong. That's about as algebraic, that's n squared, right? Because the n's cancel. That's about as algebraically simple as we're going to get. We're not going to get much simpler than that. So now we somehow, at the end, desperately need 8 over n squared to be less than epsilon. And so here's where we might go and do a little bit of a scratch work on the side. So here I'm anticipating that the proof is about to end soon. So I'm going to put my less than or equal to over, it's less than epsilon over here. And then I'm going to do a little bit of scratch work. I'm trying to minimize the amount of unused scratch work in this proof. But I need to reason about whether I could know for any reason that 8 over n squared is less than epsilon. And so I'm just going to do a little bit of simple algebra with this thing in order to figure out what this entails about n. So multiplying both sides by n, notice that you can't just willy-nilly multiply inequalities by values. Sometimes the inequality flips, but n is natural and therefore positive, and therefore it doesn't change the direction of the inequality when I do this. I'd like to know something about the value of n, and so I'm going to solve for n here. First, I'll divide by epsilon. and then I'm going to take square roots. Now, square root is an increasing function, and so when I take square roots, it doesn't change the direction of this inequality. So that's n greater than the square root of 8 over epsilon. So my scratch work has revealed a little bit of algebra, and notice that that all of these steps are reversible. I can square both sides, knowing that all the values are positive, without changing the direction of the inequality. I can multiply both sides by epsilon, knowing that epsilon is positive, without changing the inequality. I can divide both sides by n squared. So this statement that I need at the end here is equivalent to this statement here, which gives us our last step of the proof. We can say 8 over n squared is now less than epsilon, with the requirement that n is greater than the square root of 8 over epsilon, which is our last and our weirdest requirement about n, which as yet we have no justification for. But that's okay. We don't have any justification for the other three requirements here either. N needs to be greater than 1, n needs to be greater than 24, n needs to be greater than 2, and now n needs to be greater than the square root of 8 over epsilon. So if we should be so fantastically lucky that little n would just happen to be greater than all of these particular values, then we would have the proof as we need it. We would have this thing less than epsilon. Notice, because of the strictness of the way the relations have been chosen, they all chain together to affirm that this guy is less than epsilon. But why would we ever suspect that n would satisfy all of these inequalities? Well, we would have the freedom to choose to assume that. So let's go back to the original, to the beginning of the proof. The proof structure begins, let epsilon be greater than 0. Choose cap n to be some number that I don't know, and I'm allowed to choose it so that it depends on epsilon, but otherwise I just, I have to choose it. And then we're going to let n be natural, and then we have the freedom here in this proof to assume that little n is greater than cap n. Basically, this assumption, together with our free choice of cap n, gives us the opportunity to assume away that n should be greater than, particularly greater than, well, anything we really want, so long as it depends upon epsilon. Now, you may worry that I've assumed that little n is greater than not one thing, but 4 separate things here, right? 1, 24, 2, and square root of 8 over epsilon. And that's true. I've assumed 4 different greater than conditions on little n. But that's okay, because, well, one of these is the greatest, right? Now, I just need to assume that cap n is the greatest of these 4 things. Now, how do I write that down? Well, it looks like 24 is the greatest. Maybe it is, maybe it isn't. Maybe the square root of 8 over epsilon is the greatest. I mean, I know that 1 is not the greatest because 24 is bigger, and 2 is irrelevant because 24 is bigger. But I don't know whether 24 or square root of 8 over epsilon is the greater number. So, but nevertheless, I have to pick n to be the greater of those numbers. And, well, that's okay. I don't have to know which is greater in order to pick n to be that. I just pick n to be the maximum of the square root of 8 over epsilon and the particular value 24. Notice that it does depend on epsilon, and also it has this other particular value 24. Now, at this point, when I assume that little n is greater than cap n, I'm assuming that it's greater than the maximum of these 2 values. I could put 1 and 2 in the list too and take the max there if I wanted. I'm effectively assuming that little n is greater than the maximum of two values, and therefore it's greater than either of those 2 values. And so I know then that little n must be greater than 24, it must be greater than the square root of 8 over epsilon, it must be greater than 1, and it must be greater than 2. And so all of these asterisk comments here become facts in context. And they don't have to be rewritten. They become consequences of the fact that little n is greater than cap n. And they become, in place, justifications for each of these steps, right? This is no longer a logical borrowing act. This is the justification for this step because n is greater than 24. Why is n greater than 24? Because we assumed that it was by choosing this value n this way and then assuming that little n was greater than n. So this is how we use some very complicated algebra to produce a proof of sequence convergence for a given algebraic function, particularly a rational function, but it works for all kinds of functions. I suggest this work in this way because it helps us to manage the work and write the proof just once, which is a big advantage. Let me remind you that we can, at every stage, let this thing expand a little bit, but without destroying its basic nature. Here, we didn't want to destroy the fact that this was a cubic. That was important to us. So the work expands at every point, and then we get the answer. So that's how we do an algebraic proof of sequence convergence.